4. So this unit is on kinetics, and the majority of the unit is going to be brand new, and so we don't have a lot that we need to review from Chem 1, but there are a few things that we're going to review. The first thing is we're going to talk about the collision theory, and I'll explain in a minute how this relates to kinetics and what kinetics actually is. But so in Chem 1, we talked about the collision theory or the collision model, and there were 3 requirements or 3 components for this model that dictate whether a reaction will take place or not. The first one is that the molecules must collide. So there must be a physical collision between the molecules in order for the reaction to actually take place. So if you look at the picture at the top, this green atom and this green atom, they must physically collide in order for this reaction to happen. And if they don't collide, then this reaction is not going to happen. And then the second part is not only do they have to collide, but they have to collide with enough energy. And we will talk about later in the unit what that energy is called, but some of you may remember it's called activation energy. So the collisions must have enough energy, and that amount of energy is going to be different for every reaction. And then I'm going to put a little note that it's activation energy, just as a reminder of that term that we talked about. And if it doesn't have enough energy when it collides, they'll just bounce off each other and the reaction won't happen. And then the third component is that the collisions must take place at the correct angle. And orientation angle, that means if this green atom here were to come in at this angle, that reaction wouldn't happen because the correct orientation or the correct angle must be in a straight line like it's showing in this picture. So those are the 3 components. If one of those parts of the collision theory don't happen, then the reaction is not going to take place. The second part from Chem 1 that you need to remember are the 5 factors that affect the speed with which a reaction can happen. And they are temperature, concentration, whether or not there's a catalyst. This one is surface area. And the final one is stirring. And you need to be aware of how those will affect the reaction rate. So whether doing whatever it says here is going to cause the reaction to go faster or slower. And so if we go through these examples, and so if you increase the temperature of something, that's going to increase the reaction rate. So there's going to be a higher temperature, means the molecules are going to be moving faster, which is going to mean there are more frequent collisions in addition to there being more energy behind those collisions. And so that's going to increase the reaction rate. The reaction will happen faster. The second one, decrease in the concentration, that's going to decrease the rate, so it's going to happen slower. Decreasing the concentration means there's going to be fewer molecules to collide, so the collisions won't happen as frequently, which is going to slow the reaction down. Adding a catalyst increases the reaction rate and happens faster, and the way that a catalyst works, as a reminder, is it's the lock and key analogy that oftentimes is used with enzymes in biology class. But what a catalyst does is it takes the molecule and it forces it to be in the correct orientation. And in doing that, it lowers the amount of energy that's needed for that reaction to happen, which then causes the reaction to happen faster. The fourth one, grinding solid reactant into a powder, that's going to increase the reaction rate. And the reason for that is there's going to be more available sites for those collisions to happen. If you think about a giant sugar cube, the only collisions can happen on the surface. But if you take that sugar cube and grind it into powder, there's going to be even more areas where the collisions can happen. And so grinding a solid reactant into a powder is going to make the reaction go faster. And the last one, stirring, that one is also going to increase the reaction rate because you're forcing the molecules to collide. And obviously the opposite would be true. If we decrease the temperature, you would slow the reaction down. If you increased the concentration, you'd speed it up. Now, instead of saying taking away a catalyst, we would say add an inhibitor. An inhibitor is the opposite of a catalyst, so an inhibitor would slow the reaction down. Not grinding it into a powder or not stirring it would be the options. So keep in mind, those are the 5 ways that you can affect a reaction rate. So how fast or slow a reaction happens. And the final thing that I'm going to review from Chem 1 are these reaction coordinates. Let me move this. So if you remember these reaction coordinates from Chem 1, you have to be able to know how to label them, and you have to be able to know how to calculate these 5 things here at the bottom. And if you remember, we talked about forward reactions and reverse reactions, and we'll talk even more about that next unit when we get into chemical equilibrium. But basically, a forward reaction is your typical left to right reaction, reactant to products, and the reverse reaction is just the opposite. It's kind of going from right to left in a typical chemical reaction. And so if I am labeling this with these 5 components here at the bottom, if it's the forward reaction, this here represents the reactants. This line represents the amount of products that the reactants have. And so if we then take those and read the graph, the reactant energy is going to be 80. And if we look at the unit, it's going to be kilojoules. For the products, it's 160 kilojoules. The transition state is this point up here. It's the point at which all of the reactant bonds have broken and none of the product bonds have formed yet. So it's exactly what it sounds. It's in a transition state. We are transitioning from the reactant compounds to the product compounds. And so in this one, it is 240. The activation energy, again, is the amount of energy it takes to get the reaction going. And so the place that we draw it on the graph is from the reactants to that transition state. And pretend like that's a straight line. That's the activation energy. And if we're wanting to calculate it, you would take 240 and subtract 80. So that would mean the activation energy of this forward reaction is 160 kilojoules. And the delta H is the difference between the reactant energy and the product energy. And so that we would label right here. And it's always products minus reactants. So 160 minus 80 would give you 80 kilojoules. Now this is a positive number, so just as a reminder of exo and endothermic, if you have a positive delta H, that's endothermic, meaning the reaction, the system is drawing energy in, it's absorbing energy from the surroundings. Now if we look over at this one over here on the right, this one is looking at the reverse reaction. So we're just going to kind of flip the graph and label everything backwards, if you will. And so instead of the reactants being here, now the products are there. And instead of the products being here on the right, we now say it's the reactants. And so down here, the reactant energy is now 160. The product energy is now 80 kilojoules. The transition state is still in the exact same spot. And so that's going to be 240 kilojoules. The activation energy is from the reactants to the transition state still, but because we've moved the reactants, it's going to require less energy to get the reaction going because the reactants have more energy. So the reactant, the transition state in this case, the activation energy is going to be 240 minus 160, so that's 80. Oh, forgot the 0. And then the delta H, still in the same spot. It's between the reactants and the product energy. Again, it's products minus reactants, and so 80 minus 160 gives you negative 80. And it should make sense that if the forward reaction is endothermic, the reverse reaction is going to be exothermic. Now, I've mentioned looking at these graphs, endothermic and exothermic, and that deals with thermodynamics, which is not something that we're going to be talking about in this unit, but I wanted to show you how these particular reaction coordinates, how they relate to what the unit is that we're doing. And so if I draw 2 vertical lines here, pretend like that's straight, and then one here. And so the stuff that's happening on the outer parts, this area and this area, dealing with the reactants and the products, that's thermo. And remember, whenever we look at anything in thermodynamics, it's always a state function. So it's always looking at where we start and where we end, and it doesn't matter how we get there. And so the stuff on the outsides of these reaction coordinates, that's thermodynamics, which we'll talk about in a later unit this year. But the stuff in the middle, the pathway, how it gets from point A to point B, all of this stuff in the middle, that's what kinetics is all about. And so in this unit, we're going to be focusing on this middle component, how it gets from the reactants to the products, the pathways with which the molecules go in order to have a reaction go to completion or go to some point of equilibrium. And so that's how these potential energy diagrams or these reaction coordinates play into what we're doing in this unit. And that is the introduction for kinetics.